Welcome you again. In this video, we'll learn the concept of ADC in Atmega 328P based Arduino board. So basically, what is analog and digital signals? So analog signal is a signal having continuous value. They can have infinite number of different values. For example, temperature, pressure, displacement. So this produces analog values and which is having infinite numbers. So if you see the example temperature, so there will be a uh, change in temperature, it will produces the change in the output voltage. So that value will proportional to the temperature, but it is having infinite value. There is a lot of change in the output voltage level. So these type of signals are called analog signals. And then what is digital? So it is a signal that is having a finite value. So digital signals are not continuous. They usually produce in binary representation, that is in 0 state or in 1 state. So there will be only two numbers 0 and 1. So this is example, it can be represented with 1 and 0. So on state, or we can say off state. So these are called digital signals. So analog signal are continuous and digital signals are in two modes or two state 0 and 1. So this is what the basic difference. Now what is analog to digital converter? So if you see the block diagram of analog to digital converter, so it is having these are the components. So input analog signal is given to sampling or sample and hold circuit, then quantization circuit, and then encoder, and finally we get the output digital signals. So let us see one by one the function of these blocks. So what is sampling or sample and hold circuit? So this analog signals are given input to this block. So it will sample over the period of time. It samples the signals. Sampling function produces the train of impulses. So it produces the impulses that has some value only during present time instant and 0 elsewhere. So for example, the there in different instant it is having a different values, and if it is not there, so 0 in the remaining region. So it basically multiplies the analog signals to produce the sample signal. Then it is called discrete signals. So this discrete signal is faithful representation of the input analog signal. So that is what the function of sampling. So it samples basically the train of impulses for this analog signal, and it is given to the quantization uh, block. In quantization, the signal amplitude divided into discrete level or quantization level. So it amplitude signal amplitude divided into quantization level. These discrete signal are usually in power of 2. So the binary representation signal becomes easy. For an n-bit number, the number of quantization level is 2 raised to n. And quantization will round up each sample to its nearest predetermined standard value. And this process is called quantize signal. For example, if we divide the amplitude into 4 equal levels, then that 4 equal levels, that is equal to 2 raised to n. So that therefore n becomes 2. So because 2 raised to 2, that will be 4. So 2 therefore the 4 quantization levels can be represented using 2 bits in binary. Now this example, it will be in terms of the digital code or levels. So it will divide in 4 levels. So level 1 will be 0 0, the 0 value, and the level 2 will be 0 1, that is 1. Level 3 becomes 2, that is 1 0, and level 4 becomes 3, that is 1 1. So these are the binary code or levels for this uh, analog signal. So this is called the quantization. Quantize the signals. And then the last step will be the encoder. Now this encoder converts the quantized signals into an n-bit digital word. This process is called encoding. The encoding process gives as a digital output that can be used by the digital system for further processing. So encoder basically gives the output digital signal for an n-bit word. So if we see the full process in the diagrammatically view, so this analog signal, which is in terms of the curve or the various level of this signal, then the sample signal, after the sampling circuit, it will generate a sample signal. So this will be the different values for the sample signals, and then at the end of encoder, so there will be a digital code 00011011. So this is digital level 1, 2, 3, 4. So this is how the analog to digital converter converts the input analog signal into the output digital signal. This is generalized block diagram for analog to digital converter. So it is having three elements: sampling, quantization, and encoding. Now let's see the shape, size, and resolution. The entire input voltage range from 0 to V reference is divided into number of sub ranges called steps. So this voltage range, analog voltage range, is divided into number of sub ranges called the steps. Each step is assigned a single output digital code. So suppose there are 10 steps, so all 10 steps will have a different output digital code. The resolution of the ADC is given by V reference by 2 raised to n. So this reference voltage divided by 2 raised to n, where n is called the number of bits. Previously we have seen is 2 raised to n. So n is called the number of bits used to represent the signal. For example, an ADC with bit size 10 bits and the V reference 5 volts, the total number of steps will be 1024 and the resolution will be 4.88 millivolt. So it will have 24 steps with 10 bits and the voltage is 5 volt, then it will be having resolution of 4.88 millivolt. Now the most popular type of ADC is successive approximation type of analog to digital converter. It is having these blocks: comparator, the SAR, successive approximation register, then DAC, digital to analog converter. These blocks are present. So basically how this SAR operates, the comparator compares this analog input voltage with respect to the output of this DAC and gives the signal to SAR. The start of the conversion command also given to SAR, and then clock signals will be given to it. After the conversion complete, it will generate the end of conversion signal, and the digital signals will be output for this SAR output. So D1 to DN from LSB to MSB. So successive approximation register SAR receives the comparator output clock and the start conversion signal and produces an n bit of digital output. So basically how it operates, as soon as it receives the SOC start of conversion command, all these SAR output will be set at 0. Then it will compare the output with the analog input signal which is received at this point. And then comparing, it will generate the output signal. So it will be high or low, depends on the condition. And then SAR will generate the digital output from their output. In response to this comparator, the MSB, the most significant bit, and the LSB will be generated. So whenever the comparator will generate the high, so it will give D1 as a high, and whenever the comparator comparison between these two will be low, then it will generate the low signal at the output. Now the advantages of SAR. The conversion time is equal to n clock cycle period for an n bit ADC. Thus the conversion time is very short. For example, for n bit ADC with a clock frequency of 1 MHz, the conversion time will be only 10 microseconds. Conversion time is constant, independent on the amplitude of analog signal V. It is also having some disadvantages, like the conversion time is more as compared to flash type ADC, and the circuit is more complex. Application usually it is used in the microprocessor based data acquisition system, but it is DS is most popular in various system also. Now ADC pins in ATmega 328P. So as we have discussed in the previous video also, the analog, the general purpose input output of this ATmega 328P microcontroller. These are there are 6 analog pins available for port C, PC0 to PC5. So these analog pins ADC0 to ADC5 available for connecting the analog input. Now the features of the ADC. It is the resolution of 10 bit. The conversion time is only 13 clock cycles. It has 6 multiplexed single-ended input channels. The accuracy is plus minus 2 SSB, least significant bit, and the conversion time is 13 to 260 microseconds. Temperature sensor you can connect as an input channel also. Free running or single conversion mode. The voltage range from 0 to VCC. VCC is the supply voltage to the ATmega 328P. So that is same for ADC also. So 0 to VCC. And sleep mode noise canceller is available for this ADC. And interrupt on ADC conversion complete. It is available also. Now let us see an example to write a program to read analog input on pin A2 at voltage 5 volt and print it on the serial monitor of IDE. So this is the Arduino. For example, 10 kilo ohm resistor is connected at pin. Here it is not there. Pin analog pin. So there will be a analog pin is there. So this suppose this A2 is there. This analog pin A2 is there. 10 kilo ohm resistor is connected to plus 5 volts. Then we have to write a program to display analog inputs on the serial monitor. So let us see the program. So while setup, you have to begin the baud rate. So it will initialize the serial communication at 9600 bits per second. Serial begin 9600. Then in while loop, we have to initialize the pin, or we have to read the pin. So integer value analog read at pin A2. So it will read the input at A2. Then the command is there, float value that is multiplied with 5 by 1024. So just we have seen this formula to convert analog reading to voltage, because 5 volt is the reference voltage given here, and this 1024, these are the total number of steps for 10 bit, as it is a 10 bit ADC. So it will be a 1024. And serial print ln result, so it will display the result on serial monitor. So serial monitor, as we know, it is a inbuilt in the Arduino software IDE, so we can see the result on the serial monitor. As we change this 10 kilo ohm resistor, so it will change the output, and that we can see on serial monitor. So this is what the program of analog input reading. Okay, thank you for watching this. Thank you.